Welcome and thank you for downloading this TU Delft podcast.
Okay, my name is Jos Sinke. I'm standing here in front of you as second lecturer in the first part of this introductory course. Together with Professor Hoekstra, we give the A and B section. That's the general introduction. Probably he has told you that in a few weeks' time, you get a more or less overview of a lot of important things. And in other parts of this introductory course, you will be informed about details. So one of the things you get later on is, for instance, you get something about aerodynamics. I tell today something about aerodynamics, some first principles. But later on you will see much more in detail. So I only do very shallow depth knowledge, but nevertheless I think it is very worthwhile to start with. If you do have questions during my lecture, don't hesitate to raise your hands and I will try to answer. I do not know maybe answering any question, but I will try to do so. And also what I would like to start with first is two comments. What I learned from Professor Hoekstra, there were quite some questions about assignment 3.8 and 3.11. Is that right? He gave you some questions to work on. And at the end of the second hour, let's say 10 minutes before or 20 minutes past 10, he will be here to have a brief chat with you about these questions. Preferably first 3.11, and if there's time left, also 3.8. Yeah? Another comment is, he also told during his lecture about ballooning that there was a student from mechanical engineering who was going to do a test to send up a balloon to the rim, to the edge of the atmosphere, trying to. And he gave you a link, a network, an internet link where you can watch, where you can view it. Well, what he said is that it is on Sunday, this Sunday, at about 12 o'clock. He will start his experiment. So if you are interested, would like to see it, that's the time at least to turn on your PC for that. Yep? Questions? Okay, then we will start. Today I will give a talk about some flying capabilities of aircraft. First I will start very briefly with some historic overview, a few pictures about that. After that I will tell a little bit how aircraft are flying, what airfoils we are using, and later on I also will tell a little bit about drag, about lift, about weight, about thrust, these kind of forces. Yeah? Okay, I hope this works. Maybe it's in the on mode. No, that's a pity. Okay, so first a very short historical overview. By the way, all the information can be found in these chapters. I put this presentation afterwards on Blackboard, so you can see it again and you can look for the chapters and paragraphs in your book. You see here a number of persons who were important during the first years in flying. Some of them are Dutch, most of them are non-Dutch. Any familiar faces you see? The third one is? Santos Dumont. No. I know that's also, but that guy is not in the list. Yeah. That was a Brazilian guy who, yeah. The Wright brothers, yes, they are in the list. Who? Second and third. Okay, this is Wilbur. This is Orville Wright. That's correct. That's right. More questions? More familiar faces? Charles Lindbergh. Which one? The fifth? That's not Charles Lindbergh. Chuck Yeager. Yeah, you are correct that was his achievement, but he's not in the list. Okay, maybe I can give you the other names. Indeed, these are the Orville, the Wright brothers. This is Mr. Cayley, and maybe I can put the names already in there. Mr. Cayley was one who never built an aircraft himself, but he was in the mid of the 19th century, 1860, about that time. He was the first one who realized that you have to disconnect the flying capability, the steering, and the propulsion of a flying object. All the others were working with wings as birds, where everything was incorporated. He was one of the first who said, well, you have to disconnect it. You have a function for flying, for the lift, one for the propulsion, and so on. These are the Wright brothers. This is Mr. Langley. We know you hear that name also in Langley Air Force Base, and also Langley Research Center in the United States. He's also a very famous guy in the United States who did a lot in aerospace in the early 20th century. He was, a couple of weeks before they had their first successful flight, he was also trying, but he failed. If he had success on that date, we wouldn't have known these guys, only this one. That's luck, that's how it happens sometimes. And these two guys are Dutchmen. Well, you can already see this is Mr. Fokker. I think one of these, in these days you have a celebration. 100 years ago he flew around the church in Haarlem. And I think there's a lot of activities, I think this week or next week, but I'm not quite sure. But if you look on the internet, you see that there's a lot of symposia and speeches and so on about this feat. Last one is Mr. Plesman. Does someone know what his contribution to aerospace is in Holland? Founder of Royal Dutch Airlines, KLM. Yeah, that's the one who started the KLM. Okay, these are some faces, just for the these guys were very important in the early ages. I will show a few more. This guy is also, I hope, more or less known by you, and that is Mr. Lilienthal. He's German. And as you can see, he lived at the end of the 19th century. And this guy did a lot of work, a lot of experiments with kites, kite type of things. As you can see, type gliders. He never worked with engine-propelled gliders. That was, well, he died before he even could start on that. But he did a lot of tests with a number of gliders to perfect, to optimize the flying capability, the lift capability of these gliders, these kites. As you can see here, he made about 2,000 flights. He had his own hill in Berlin. He made a hill from which he could run off, run downwards, and then take up speed and then glide with his glider. Largest distance, about 250 meters, so that's pretty long. We only have, from his efforts, we only have pictures. You can see here why, because the film was invented just before he died. So, few of his designs you can see here. These are from a museum in Berlin. He did a lot of good work. His reports, his stories about flying also were spread through journals, and also the Wright brothers, for instance, read his stories and were, well, motivated by his stories. So sorry. And if you look nowadays even at the gliders we have, well, it's more or less descendants, of course, much better, but descendants of his first ideas. Nowadays we have glide ratios, as you can see here, 17:1 and 20:1. I don't know what, in his days it was somewhere between 5 and 10. So that has been improved significantly. What I said also for Mr. Lilienthal, he had his own hill and he was running downwards. Does it make sense in which direction you are running? Okay, so we are always trying to run against the wind. You are looking for airspeed. That's important. And you will see that later on also, if you look, for instance, at aircraft flying around nowadays, you see that well, here you see some numbers. But even today, aircraft taking off and landing always as much as possible against the wind. Yeah? So ground speed is very interesting for the passengers because then they know how fast and how quick they arrive at their destination. But for the aircraft itself, for flying, of course the speed of air is most important. Okay, let's see whether this works. This is a small film about a few old designs. Maybe it's... This is not understood. Well, this is either. For some, I can understand how you more or less think, but some of them are really, well, this is also. Some kind of harvesting machine or something like that. You see, still a lot of people try to connect the propelling and the lifting device, which I said Mr. Cayley already told in 1860 that you should divide them. He's lucky. He's lucky. He can swim. This is something about rockets. Liquid propelling, well. He has a little bit burnt ass. But he's trying again. Well, this guy mounted a wing on top of his car until it fell off. Well, this is a picture of the first flight. No, not again, not again. No, not again. Please continue. Yeah. Other way around. Thank you. So, in the end, this was the historic moment, December 17, 1903. Yeah. We can also ask about this, but don't study it too intensively. Don't study it for all the dates and so on. There's a chapter, I think the first chapter in the book, that's about some historical background. I advise you to read that. I remember that in one of the exams in previous years, I made 1 or 2 multiple choice questions. So then you have 4 alternatives, and usually 2 alternatives can be skipped quite easily. And with some understanding and reading it, you can select between the remaining 2. Yeah? So there is indeed sometimes, but not an open question. I will not ask all kind of stories and so on. Usually in a multiple choice setting. Okay, this is the main event, and again, this is a small film I will show. This is from a couple of years later, and there you can see the Wright Flyer flying, and it's very nice. Maybe I will show it twice. First, have a look at it. A lot of discussions beforehand. The aircraft positioned. And as you can see, it can fly rather smoothly. Of course, this is not the one from 1903. It is an updated one, an improved one, but nevertheless it looks much similar than the first one. What you see, maybe I can tell beforehand, what you see, and then I will run it once more, is that the aircraft is put on rails. It does not have wheels, it's put on rails. And there's also a tower with a counterweight, which is pulling the aircraft, so you get in a very short time sufficient speed, so he has enough lift. On skis or something like that. He has some type of skis, but not wheels. So once more. Well, here you see the track. This is some kind of rail track. And he has some 1 or 2 wheels in order to keep it balanced, but those are left on the ground. And there he's flying. Marvelous. Okay, these Wright brothers, it was not a coincidence that they came with the first flying aircraft. Of course, there were other persons and groups also working on first aircraft. But these guys at least had some good potential, because they had, for instance, some shops, some workshops where they can work with tools, with materials, and so on. Again, as I told before, Lilienthal, with his stories, motivated them, inspired them. And also, they built very simple wind tunnels to test some of their designs. The wing shape, the propeller, has been tested in a very simple wind tunnel by these guys. Well, of course, the readiness of technology, if they had not been the first one, I think 1 or 2 years later, there was another one who was the winner of this contest. Here you see some of the features of this aircraft. It's not that light. Wingspan of about that. Wing area of about 48 square meters. And again, the longest distance the first one flew was about 260 meters, and it took them almost 1 minute. If you calculate that, then you have a ground speed of about 15 kilometers per hour. So it's very, very slow. So probably they also had some significant headwind. Okay, later the Flyer has been improved, better wings, better engines, and so on. And the one you saw flying in one of the films was an improved version. Well, here, if you look into detail, in a picture like that, you can see how flimsy such an aircraft is. You see a lot of, wooden frames. There's some canvas or linen covering all these ribs. A lot of wires to stabilize the whole thing. And some of the wires are also used for steering, because they don't have ailerons as we have nowadays on our aircraft, but they pulled on wires. They just twisted the wingtips just by sheer force. The flying direction is in this direction, so the elevators here in front of it are some kind of canard type versions, canard type designs. But it's very flimsy, very fragile looking, and well, indeed, there were in many cases a lot of accidents with the first aircraft, because most of them were that type of manufacture. Well, if you look at what the influence was of these first aircraft, well, the most important fact that they were recognized as the first flyers was that they had a powered flight and a controlled flight, and it was a heavier than air flight. These three items are very important. Of course, you have seen with ballooning that before that there were also other flights, but in many cases with balloons or lighter than air vehicles. Yeah. Also, Lilienthal, he was flying around with a heavier than air kites, but it was not powered. Definitely he had some control of it, but not powered. So that's the difference between the other ones. As I said, the twisting, the flying, sometimes they did by twisting parts of the wing. That's called wing warping. Yeah, just by rolling, they did it by some wing warping. Later on, Mr. Curtis and Farman, a few years later, they developed the ailerons, movable small surfaces attached to the wing. And that helped to steer much better. And of course, they also did some contribution in wind tunneling. You need some wind tunnels to test before you go to fly. And it was also rather new in these days. Well, if you now compare this aircraft with our current aircraft, then you see a huge amount of differences. Yeah? This is one of the latest designs, the 787 Boeing concept, and even nowadays you see a lot also shaping of these wings. It's not a straight wing anymore, but completely computer designed. In many cases made by composites. You can tailor them as you like, and so on. So in 100 years there's a huge revolution in that. Again?
Do you think it's going to be like mono wings soon?
The question is whether I think there will be mono wings soon. It's hard to tell. I'm not blended wing, what you mean, eh? Yeah. Blended wing concepts, that you have no fuselage anymore, but the wing is thick enough that also people can sit inside the wing. Technically, I think it is possible. There's no doubt about that. You see also the B-2 flying bomber. So, but there are a few obstacles I think they still have to do. First of all, interest the public for it. because as soon as you are doing that, you have a square inside your aircraft, and window seats are not there anymore, only very few. And I think a lot of people still would like to fly seeing maybe or sitting next to the window or are able to look outside. Because we also, it has been discussed in the past whether we could remove all these windows, but that's out of the question. Because these windows, as you see them here, are really a pain in the neck for a lot of engineers, because you have to design for it. And if we could, as aircraft engineers, remove these windows and say to people, well, you have a LCD screen in front of you, look at that. If we could remove that, that could save a lot of weight, and we could fly much more efficiently. But so far, no one dared to do so. So also a step to blended wing, that's one of the reasons. Also, if you look for a cylindrical fuselage, that's for internal pressure quite an optimized concept. As soon as you have a flat shape, then for pressure it's not an optimized shape. So you have to compensate a lot with materials. We have new materials nowadays which can do the job, but these materials are maybe stronger and lighter, but part of the benefit you have in these materials are sacrificed by the non-optimized shape. So you have much better materials, but you do not use them in the optimal sense because you have these kind of things. So technically, yes, if it is introduced quickly, I'm a little bit hesitant about that. Yeah? Long answer, short question, long answer. Okay. But there was room for questions, as you can see. More questions? How did the wind tunnel by the wool? I'm not quite sure, but I can imagine it was an open wind tunnel. So you have some tube with some fan on front of it, and this is blowing some air through a tube. Because the closed wind tunnel only, I think, appeared 10 or 20 years later. So the closed loop wind tunnels, as we have nowadays.
Do you think it's more efficient to have ground effect planes going over the ocean from Europe to America?
Ooh, another question. You have a lot of these. I don't know. I know that winding ground effect can help you a lot by flying more efficient. But realize an ocean is not just waves of 1 meter, but usually you have waves sometimes of 6, or sometimes even higher, and then it becomes very complicated.
With radar? Bigger the plane, bigger waves.
Yeah, but I can see it for small areas and in over waters where you have where the waves are not very dominant. But between Europe and the United States, for instance, you have in many cases a lot of storms and a lot of high waves. So. Why does the Wright Flyer have these front ailerons? That's the question, eh? I think that was their choice. They had some vertical steering in the back and some horizontal steering in front. But don't ask me why they did it like this and not in the... Answer is given in the book. Yeah, that could be maybe a reasoning for them, yes. That could be maybe. Whether it holds, I'm not quite sure. Last question. Yeah, you?
Why don't we have hypersonic fighters, even though we have the F-22 going Mach 6 and we have the Concorde going almost Mach 1.5 like the 80s, but now it's almost 2000 we're stuck with 1970.
Why don't we have hypersonic jets? And we are still... Yeah, yeah. I think it has to do with economy. because hypersonic jets are very short flying times, but still I think you have much more energy consumption for such a flight. And I think still the economy dominates this choice. I don't see at the moment also supersonic flight, hypersonic flight. I'm very in doubt about whether we will see that in 10, 20 years' time. And that's because of the fuel consumption. Hmm? Another one. Yeah, yeah, because obviously that's the most efficient way of flying. Hmm? Yeah, but for how many people is time really a hot issue? Yeah, okay, if you go on holidays, who says, I would like to be in 1 hour to Spain instead of 2 hours? There are. Okay. But that's a little bit... And are you then willing to pay 2 or 3 times the ticket price? Most of the people don't. Look at the Concorde. We had a Concorde flying to the United States. And there were people flying there. But the ticket price was 3, 4 times higher than a common ticket price. And a lot of people say, well, 3 hours or 8 hours, I take 8 hours for a much lower fare. They had a commerce, yes, indeed. But and maybe there will be some supersonic flight in the future. But in my opinion, but okay, can I ask everybody else? I don't see it will overtake all the flying we are now doing today. Yeah? Okay. Questions? We already had the... Okay, next subject. Where am I concerning time? Okay, I have to speed up a little bit. What I would like to do is to talk about this equilibrium, about these forces. If an aircraft is flying at constant speed, at constant altitude, you have a force equilibrium. Yeah, the aircraft has a specific weight, and that is counterbalanced by the lift. It has a specific drag, and that's counterbalanced by the thrust of the engines. Well, those are four very simple forces I will address in the coming slides. Okay, so realize this is true when you have constant speed, constant altitude. Okay, if we look at the lift, the main portion, the majority of the lift is created, of course, by the wing. Small contributions you also have from the tail surfaces, but 90–95% is coming from the wing itself. The weight, most of the weight is concentrated in the fuselage. In the fuselage you have your main structure more or less, but also all your payloads, cargo, passengers and so on. So about 50–60%, sometimes even more of your weight is concentrated in that fuselage. The drag is induced by well, the fuselage, which has a significant front area, but also the wings, also the tail surfaces, and so on. And of course, the thrust is provided by your engines. Okay. One of the main rules in aerospace engineering is you always need to look for lightweight aircraft. Why? Take another one, sorry. Yeah.
Yeah, if the aircraft is lighter, you don't need as wide wings, and if you have shorter wings, the drag is smaller as well. And that makes it lighter as well.
Yeah, but that's an optimization, and once you have now let's first look at other asanas. Yeah.
maybe it's cost efficient to fly at weight instead. And the goal is to transport as many payload as possible. So the larger your airplane is, the more goods you can transport.
Okay. Most efficient way to fly.
Well, less weight, less lift needed, so you need less thrust, which is going to be like cheaper.
Yeah. Less weight, less lift, less drag, less thrust, and so on. Last? Okay. Okay. Well, actually there are two answers in this. First of all is indeed the loop in which you have less weight, less lift, less drag, less thrust. And if you have less lift, you can have a smaller wing. If you have less thrust, you can have a smaller engine. That means indeed, again, a decrease in your weight and so on. That's a so-called snowball effect. At the end of this course, I will come back to that. The other answer to it is that you have the weight of your aircraft consists actually in three parts. And maybe I can also start to put forward this answer. And that was the answer actually I'm looking for in this case. Three main components: the empty weight, that's the structure, all the systems, etc., etc., the fuel, and the payloads. And here, if you can see, if I decrease this one, lighter structures, lighter aircraft, I design and build lighter aircraft, better materials, and so on, this is decreasing. And that makes that we can, for the same takeoff weight, increase one of these, or maybe a combination of it. And more payload means more revenue. And more fuel taking on board means that we can fly longer distances. Yeah, so that's why there's a continuous incentive to try to come up with lighter structures, lighter aircraft. So we go from metals now to composites, or combinations of metals and composites. That all has to do with that. Improving materials, improving structures, and so on. Okay, so in general you could say we are improving the performance. Let's go to the first force. First I would like to talk about the lift of an aircraft. I don't know whether you have seen this equation already before, but this is a general equation of the lift of an aircraft, and I think you will see them plenty of times. So in the end you can dream it, and that's what we would like you to do. You have here a number of parameters in there, variables in there. The first one is the lift coefficient. And that's a constant value which matches this one with that one. But it is not without meaning. This CL value is a very important one because it tells how the wing performs, how efficient the wing performs. I will come back to that in some other slides. This one you already recognize, that's the density of the air. Depends a lot on the altitude you're flying in. The V is the airspeed. We're not looking here at ground speed, we are looking at airspeed. And we have seen it already before, going down the hill, what makes sense, the ground speed or the airspeed? Well, for flying, for the lift, it's the airspeed. How the wind moves with respect to your aircraft. And this is the wing area, the surface of your wing, the parameter S. The platform area, yeah. So if you look on top of, if you have a topside view on your aircraft, just the surface area of your wing, that's S, wing area. Okay. So here you see a number of parameters. You know this is a force, so that's in newtons. You could ask, what is the dimension of this CL value? I don't ask you to... What's the dimension of this? It's just a value, he says. We will see. How do you tackle this? Rearrange the equation. So what you're actually doing here is newtons, for instance. And then here a kilos per cubic meters, and so on. Is that right? Yeah, that's what you mean? Okay. Well, that's the strategy. And that's a very efficient strategy. That's a calculation with dimensions, which can help you sometimes by checking your results. As soon as you have results in calculations which you are not very confident about, you are doubtful about, this is one of the tricks you can use to check whether you used the right equation, whether you used the right parameters. So actually what I've done here is Newton. This is a question mark. This is the density. This is the speed. And this is the surface area. If I rearrange that, you see I come up with a question mark without any dimension. So this is a dimensionless parameter. Again, this is some tool you could use during a lot of calculations for checking up. Okay. If we look, for instance, at an CL or the lift, but let's zoom in a little bit on that CL value, because I said it tells something about the efficiency of an airfoil, of a wing. Let's first have a look at it in two-dimensional way. This is a cross-section of the wing. And there you see that we have a so-called airfoil or wing profile. And if you look at such a wing profile, you can see a number of typical parameters, a number of typical features. First of all, the length of it. That's what we call the chord. And that has a parameter C. That's actually the distance between the leading edge, the front tip, and the trailing edge, the aft tip of the wing. What you also can see is that if we look at the center line of the profile, the center of each distance at any location, that's a curved line. It's not identical with a straight line between the front and the tip. That means there's what we call a camber in this profile. It's not symmetrical around this line. And the profile also has a maximum thickness. Well, most of the wing profiles are not symmetrical. Most wing profiles have this shaped form. And whether this thickness, how large this is, or how big this camber is, or those are design variables you can play around with. If you look, for instance, at tail surfaces, these have in many cases more or less symmetric profiles. So for generating lift, such a profile is important. Maximum thickness, yeah. Not average, maximum thickness. So by shaping a wing profile like this, you already are able to generate lift, even when this is in the neutral stand. This is horizontal if I fly horizontal. Then we have what we call an angle of attack 0. Because another way, as you can see here, if this is the flying direction, if the wing is pitched up a little bit, then we have a so-called angle of attack. And that's also contributing to the lift. So the lift of a wing is generated due to its shape, and also to its position, angle of attack. And of course, other parameters are also involved here, air density and airspeed and the wing surface. You have seen the shape profile, the profile with a camber. And those are rather complicated in many cases, also not that easy to fabricate. But we often make them, and we don't use symmetrical ones. Why don't we use symmetrical ones? We also can generate lift by our angle of attack. Yeah? Yeah, you?
Because it's more stable as a painted line, and then fighter airplanes have more symmetrical, so they're more unstable and more agile. And more
Stability, that's one. Yeah? Yeah, you? The pressure difference you are creating. Yeah, but that's also possible. You also can generate it by a certain angle of attack. So that's not. To store fuel, you get more space, maybe. To minimize drag. That's the best answer and the right answer. Because as soon as I pitch up my wing to generate lift, I also get much more drag. Yeah? And that's the reason why we often work with these shaped profiles. So in particularly for horizontal cruise, we try to have a shape of the wing which minimizes drag. Of course, we have to climb first, and later we have to descend, but the most important thing in flying is still, on long distances, the cruise flight. Okay, so drag. Realize it also minimizes drag. Well, in the past, early ages, there were very large number of different systems to describe these airfoils. What's the time? Well, I'm already in the break. I will finish this and then send you to break. A lot of different names. Everyone more or less generated his own concept. You have here the Wright designations. You have the RAF designations. Later on, from the 1920s, I think it was, there was a organization in the United States who more or less classified profiles, and from that time on you saw a lot of so-called NACA profiles, and those have specific descriptions. These NACA profiles gave a very distinct description of how a profile looked like. Well, here you see some information. That was the National Advisory Committee on Aeronautics, established in 1915. And they were not only looking at profiles, they were also looking at propellers, landing gears, aerodynamics, and so on. So they generated these airfoils, and those are 4-numbered digit nomenclatures. And here you see, for instance, one. A NACA 2412 means you have 2% camber. That means a distance of 2% of the chord length. Everything is related to the chord length. 2% at a distance of 0.4 times the chord from the nose. So this is 0.4 times the chord length. And the thickness is 12%, again, of the chord value. Well, this is a system you see is still used quite a lot. Of course, nowadays you also have other systems, but this is a very transparent and very nice way of describing these profiles. After the break, I will continue with someone else. Yeah, first let's have a break. I had in the break a few questions about camber and these kind of things. Once more. Oops, put it on. This straight line between the leading edge and the trailing edge is a straight line connecting these two. And that's, if the profile has no camber at all, is also the symmetry line for your profile. For a symmetric profile, that line is then also your symmetry line. As soon as you don't have a symmetry in your profile, we have some camber, and that's the curved line. And the curved line is nothing more than the exact middle between the top surface and the lower surface at each location. And the distance between that, you see here, there's a distance between that. The maximum distance is called the camber, is expressed as a percentage of this length. So if I do have a chord length of, let's say, 5 meters, and I do have a camber of 2%, then this distance will be about 10 centimeters. Yeah? So that's the definition of camber. Yeah? Clear now? Don't hesitate to come back. All right. I would like to say a few words about how aircraft fly, and then I need Mr. Bernoulli. Bernoulli is a person very important for airflows. What he discovered, or what he learned to tell us, is that if you have some kind of tube in which you stream air through, constant mass per time, for instance, and if the tube have different cross sections, then in very wide sections the air will flow very slowly. But in very narrow sections you are forcing the air more or less through it, so that you have a high speed of the air. So in this side, low speed, high speed, low speed again. Realize Mr. Bernoulli is talking about incompressible air. You cannot compress it. That's true for air speeds up to 300 kilometers per hour, more or less about that. At flying speeds we use today, we are not allowed to use these formulas. We have some different formulas, but you will learn them in the aerodynamics part. This is just for some basic understanding to explain how we can fly. This is one of the ways to explain it. What he said is that you have a static pressure and a dynamic pressure. This is the static pressure and this is the dynamic pressure. If I determine them at two locations, let's say here and there, position 1 and position 2, these are identical. They are constant. So this equation is constant. And what you can see right now, if, for instance, the speed is increasing, then you can also see that the local pressure is decreasing. Yeah? So a higher speed means a lower static pressure. Okay, so if I do have an airfoil, and if I have low airspeed below the airfoil and a high airspeed over the airfoil, I will have here higher pressure and lower pressure up there. So a high pressure, high relative, at the lower side of my airfoil and a low pressure at the high, so I generate a pressure upwards. Upwards pressure that's causing my lift. Yeah? So that's for incompressible airflows. Yeah? My learning curve is not that correct today. Okay, so higher velocity, lower local pressure. So lift you generate by pressure difference. And in many cases these airfoils with these camber are designed such that you already create that pressure difference. And also, I will show in a few moments, also the angle of attack has a big influence on that pressure difference. Okay. Well, you also can use the Bernoulli law to think about how to measure airspeed. Yeah? I will not ask you to do that right now, I just try to explain it. If we have a pitot tube, that's actually what it is, the air is coming from this direction, goes into this tube and comes to a standstill. So what I measure here at this location is the static pressure, the absolute static pressure. Total pressure. On the other hand, the airflow is also passing by with some speed, so the local static pressure, not the absolute one, is measured here. And you can see that's at this side of my measuring device. That pressure difference, total pressure, times the local pressure, gives me the airspeed, because I can use this equation, the Bernoulli equation again, in the case that at this end the velocity is 0, so it has no contribution. And by rearranging this one, I can calculate my airspeed. That's, for instance, the principle you can do with your static tube. Again, realize you are measuring the airspeed, not the ground speed. Okay, pressure differences. No. Gaan we nou heen? Deze kan graag. Here you see, for instance, some profile with a camber and some angle of attack. And you see the pressure distribution over the surface of that profile. You have lower pressure at the upper side, specifically at the front end, and you have some higher pressure at the lower side. You can also do that in a plot, as you can see here. You can here see the curve of the lower side, and here the curve of the upper side. And the area in between is a measure for the total lift of that profile. You can integrate it, and then you can generate lift. Calculate lift. And now I have to go here. And try to get this one, because this is a very nice link, also for you to look at it at home. I hope it is a little bit quick, yeah? Come on. Yeah. This link gives, for instance, first let's go to metric units. Rescale, yeah. This is actually more or less some kind of playing tool to see what you can do with changing the shape of the airfoil. What you see here right now is a airfoil with an angle of attack of 5 degrees. It has no camber, so it is a symmetric airfoil, and it has a thickness of 12.5. And what you are measuring here is the lift. The lift at this moment is that value. And, well, I can play around, for instance, with the angle of attack. Where's my cursor? See, you see, if I change it, let's say increase it to about 10, you can also see the pressure distribution changes that I can see in this plot, but also the value of my lift. I can also play with the camber. If I put this a little bit down, no, not too low. Again, you see changing the lift. You can also, this is about the shape. There are more items to it. I can just show you. You can flight test. Flight test, you can, with a specific profile you've chosen before, you can play around, for instance, with the speed, with the altitude, and so on. So this is typical a tool you can play with to see what the effect is of camber, of angle of attack, and so on. Yeah? So there is the link, and you can see it later on also in the slides. Probably we also use this simulator during one of the studio classroom sessions you will have. Yeah? Okay. Sometimes I made these slides with a lot of clicks, but it's not always that useful. Okay, again here you see the profile again with all these features we have seen before. NACA description. If I take two, for instance, this one and that one, you see here two curves. Which is which? Any idea? The red one is 0012. And why? Right. This is a symmetric one. It has no camber. Only has a thickness of 12%. That means it is a symmetrical profile. And at zero angle of attack, you also have zero lift. You have zero CL value. So that means you go through the origin of this plot. So indeed, the red one is this one, the other one is that one. Okay, so here you see typical CL alpha curves, and in many cases they have a large part which is linear. At some end, when you increase the angle of attack, you will see you get a leveling off, and in the end you get stall. And yeah?
Do we need to know how the NACA notation works for midterms? Do we need to be able to use it?
No, I think you should be able to, but at least it is for your common knowledge that it is very interesting to know how that's built. So that if you work a few times with it, you will see then it is very easy for yourself also to recognize right away what kind of shape it is. But it is not something that I give you a number and then you say, oh shit, what is this? Yeah? So I will try to, because usually these are still numbers you can look up into your books, and the understanding is for me much more important than the knowledge of all these small details. Yeah? But here you see, for instance, a full plot of the CL alpha curve. And there you see, for instance, that after a while you get maximum lift and you get stall. This is typical flow around the curve. First of all, it's laminar, and then you have some transition points, and then it starts to get turbulent. And we try to maximize as much as possible laminar flow, because that has a very low drag. But for sailplanes, you often see they can increase this point sometimes even up to there. But for common aircraft, it's usually 30–40% of the profile is laminar and the rest is turbulent. But that's because you have all kind of, well, rivets and small deviations, and that helps starting transition from laminar to turbulence. But that's the most favorable one, the laminar airflow. Well, here you see in several steps what happens. This is a very nice airflow, as you can see here also. When you increase, in this case, the angle of attack, the flow becomes more and more problematic, and in the end you get some delamination, disconnecting of the flow and your airflow, and then we are talking about stall. Then you lose your lift, and that's very dangerous. And here you see also there's no contact anymore between the flow and your profile. Well, I will skip that one. We have seen, if you would like to fly at low airspeeds, then you have a problem, because if you look at the lift is proportional to the density, is proportional to the wing surface, and both are more or less fixed for certain conditions. We cannot change in the meantime very much the wing surface, we cannot change very much the density, because when we are landing we are at sea level, density is, well, 1.22 or something like that, 1.25. But we would like to drop our velocity, our speed, we would like to drop it significantly. So we have actually very limited possibilities to play around. And the only thing we can do, for instance, is to play around with additional devices, slats and flaps. So sleds, for instance, those are these trailing edge devices. We can, if this is the common CL alpha curve of the wing, by adding these, we can increase the curve to higher values. That means we can have higher CL values, and that has also implications for higher lift forces, even at lower speeds. Yeah? So these devices usually have impact on the CL values. The same with flaps in front of it. These front end flaps also have an impact. And here you see, for instance, one of the pictures where you see the airflow with a flap, extended flap, how it follows and still is rather okay. No stalling at this moment. These are typical devices you use during takeoff and landing.
So why not always fly with flaps?
Because then at high speed you have more and more drag. Yeah, so it's always the balance. You need to have enough lift, but also try to have as low drag as possible. At landing and takeoff, the speeds are not that high, so the drag is not that high, but then we are focusing more on the lift, and at cruising altitude, then the drag is more dominating. Yeah? Well, you can play around a lot with wings, wing surfaces. This is, for instance, top view. Well, this is the wing surface. The wingspan is from tip to tip. The taper means how it is, the chord is decreasing from the root to the tip, and so on and so on. You have a lot of variables to play around with in the wings when you are designing wings. And you can also see here in pictures like these ones, you have tremendous amount of different wing shapes. So far something about lift. Questions about this item? Okay, then a few words about drag. Actually, you see more or less the same formula. This formula is more or less the same as the lift formula. We only have a different coefficient, drag coefficient. So the CL value is removed and is replaced by the CD. The rest of it is much alike. If we look at drag, there are a number of components in the drag. First of all, you have skin friction. This is, if I rub over this surface, you have skin friction. The air also does, and you have skin friction. Yeah. Fewer slides. I put them also on Blackboard, so please, this one. Yeah? So skin drag, that's the drag when the air flows over the skin of the wing, for instance, or of the skin of the fuselage. You also have pressure drag. As soon as air has to flow from a low pressure to a high pressure, you encounter friction, you encounter opposite forces. Wave drag, that's in case you have transonic and supersonic speeds, then you get these the pressure waves, the pressure steps. We will discuss in one of the later lectures about that. And also parasitic drive. All these devices which do not participate in lift also generate a lot of drag. As I said already, the fuselage, the engines, and so on. What we often do is that we define the drag coefficient as a zero value, constant value, and one component which is proportional to the square of the lift coefficient. You see here some parameters like the tapering and some other value. These are constant, but this is a changing with alpha. I will come back to that in a few moments. Just to illustrate a little bit some different types of drag. drag related to the shape and skin friction. You can imagine this one has almost no drag due to its shape. It's very flat, it's perfectly aligned with the stream, but has a lot of skin drag. So if there is drag, almost 100% of the drag is skin drag. This is the opposite. If I put a plate perpendicular to the airflow, you can imagine almost all the drag is directly related to its position, to the form, in this case. Well, here you see some intermediate shapes. Terug. Even wachten. Well, here you see two pictures. Such a plate which is more or less placed perpendicular in the airflow, and there you see you have a very high drag coefficient. And this is a nice, more or less streamlined profile, and there you see the drag coefficient is much smaller. Yeah, so just to give you some order of magnitudes. What we discussed so far is more or less two-dimensional in the plane. If you look one step further, you also can see, for instance, three-dimensional effects, which also cause some drag. If this is the wing, we have an overpressure below the wing and an underpressure over the wing. You can imagine that some of the air would like to escape in this direction, turn around the corner. And that is also inducing these vortices. You can see them also here in this picture. Vortices because of the airflow. The vortex is not contributing to the lift, it's only contributing to drag. So you have an increase in drag, and these are only, well, you should try to get rid of it. One way to do it, for instance, are these winglets. What you actually do is to prevent most of the airflow to turn around the corner. And therefore, adding winglets to wings can help you by fuel consumption. You get a reduction in fuel consumption by 2, 3, sometimes 5 or 6% because of these winglets. Well, here you see two lines in the left-hand side in one plot. This is what we have seen already. That was the CL alpha curve, the lift coefficient, CL, the angle of attack. And in the same plot you also see now the drag coefficient as function of the angle of attack. Realize it looks as if they are more or less at the same size, but there's a significant scale difference between these two. The scale here is 5 times smaller than here. So I just put them in one plot because otherwise you only see here a very meager curve, a very meager line. Now you see them more or less like that. I also can put them in a so-called lift-drag polar. What I do is for each angle of attack, I take the two values and put them in a plot like this. So I have, at each angle of attack, I have one drag coefficient and one lift coefficient, and I get all these data points. And when I have this line making contact with my curve here, then I have the best ratio CD over CL, the lowest value. And that means that's the value with the best flying conditions. Yeah? So usually the maximum CL/CD ratio you find here, and we try to design, for instance, the cruise flight as much as possible close to that value. And then you have a more and a good and efficient way of flying. I will skip that one. Just to show that CL/CD ratio can be very different for different types of aircraft. You see here a modern sailplane, the Lockheed U2, that's this one. This is a bird, an albatross. Boeing 747, Concorde, as you can see here. A Cessna, again the Concorde, a Sparrow, and the Space Shuttle. You see already the Space Shuttle is not that efficient in flying, but okay, it's not designed to. It's just to have some wings to come down. But here you see some typical values. And then you see, for instance, this aircraft is even exceeding an albatross. An albatross is already recognized as a very good flying bird, very efficient flying bird, but such an aircraft like this is even exceeding it. Modern sailplanes can even have much higher values. Yeah. That's an art in itself, more or less. Okay. I will have a few more words about the two other forces. We have seen 4 forces: the lift, the drag, the thrust, and the weight. We have seen now the drag, and that has to be counterbalanced with the thrust. And for flying, we have a number of engines we can use: propeller engines, piston engines, turbojet, turboprop, turbofan, ramjet. Nowadays, the Americans are, for instance, doing a lot of research in this area, the ramjet and scramjet, where you see sometimes that some experiments fail and some are successful, but, well, there's a big research ongoing on that one. Most aircraft nowadays are equipped with turbofan aircraft, and you see a picture of that here. If you are talking about a turbojet, actually that's only the core without the fan, so then all the air is flowing through the hot parts also of your engine. Because in this area the air comes in, we compress it even further to high pressures, and here we mix it with the fuel and then ignite it. And in a car you have that piston engine, you have a not constant burning process. You have some explosion, then you have a work cycle, and then you have a compression, igniting, explosion, work, and so on. That's intermittent. In this air engines, it is a continuous process. So there's a continuous burning of fuel and compressed air in the combustion chamber. The hot air is expanding here in the turbines and in the exhaust, and thereby these turbine discs are also propelling the front end. And we also have enough energy also to propel the aircraft. Yeah? That's a turbojet without this fan. Nowadays they are flying with much more efficient turbofans, and not all the air is going through the hot section anymore. Most of the air is going outside. These turbines are also propelling, also driving these big fans. And nowadays I think 6, 7, 8 times more air is going around the engine than through the engine, through the hot parts. So then we talk about bypass ratios of 6, 7, 8. Most of the air is bypassing the hot section of the aircraft. And these engines are now very efficient if you compare them to engines of 20, 30, 40 years ago. Yeah? Okay? Yeah. Again? Good question. I don't know. You should ask, I think, Mark Voskar. Mark Voskar will talk much more about engines. But about these specifics, I don't know. Usually I think they use some starter, but I'm not quite sure about that. Yeah? You hear also the answer from your colleague. He knows more than I on this area. Okay. This is also a question I would like to, for homework, you can see and the question and the answer. Think about that. One comment about weight, and then I give the floor to Professor Hoekstra, because he's already waiting there. The weight we have seen already is divided in 3 main components: aircraft empty weight, And there you can see what kind of components are in there. What's always a little bit weird and a little bit funny is also this one. If we talk about aircraft empty weight, we also include the crew and the flight attendants. Yeah. The rest is payload, and the other one is fuel. So if we minimize the weight, we can increase the payload and we can increase the fuel. Increasing the payload, more money. Increasing the fuel, longer distances. Yeah? Another way to use it, well, here you see some numbers. Another way to use it is for instance, the so-called snowball effect. We also discussed it before, that once you decrease the weight of particular sections, let's say you replace a part of the structure for a new structure which has lower weight, you can use some kind of snowball effect. Because lower weight, you need lower lift, you have lower drag, you can have lower thrust, and lower lift means a smaller wing, smaller engine, and again. So then you enter more or less in a loop like this. And with an initial weight reduction of maybe 1,000 kilos, you could end up with a end weight reduction of maybe 2,000 kilos or even more, due to that so-called snowball effect. I think I stop here and then give the floor to Professor Hoekstra for answering and looking at these questions we have seen before, from 3.8 and 3.11.
Thank you, Jos. Even inloggen op Blackboard. Kan ik het laten zien. Kijken. Okay, I got a lot of questions on those two problems. One of them was not in the solutions that we put on Blackboard, so I could have anticipated that. First of all, as you might have seen, the solutions for chapter 2 and 3 are actually based on the 4th edition. That's why some of the problems were missing. And it's also quite US-centric. They used a lot of the US units. So I'll also go into how you can easily work between those two units, because I heard some people had trouble with that as well. If I have the time, otherwise I'll do it the next lecture. But I'll look at the problems first. Who did make the homework? Okay, those are the ones that usually pass the exam. Really true. Because it all looks very simple. If you just look at the answers or the derivation, then it seems obvious. But if you have to choose yourself what to do, it's much harder. Come on. Sure. Whatever. Come on. What is he doing? Who still uses this browser, right? It should have Chrome or Firefox on it. Okay, course information. Getting there. Slowly. Module AB. Emerson solutions here. Okay. 3.11 or 3.8? What should we look at first? 3.11? Okay. Well, 3.11, the question was about the water tank. Okay. So we have a water tank. Don't know how well this works, but we'll try. What kind of program is this? Okay, still Internet Explorer. Maybe it works better on the screen. But anyway, the water tank, there were it was basically, you use different things there. You use the hydrostatic equation to calculate the increase of water pressure in a tank. An important property of a fluid compared to a gas is that a fluid does not compress or hardly compress with increased pressure. While a gas, where the molecules are much further apart, that will compress much more. So when you use the hydrostatic equation, you do not need to worry about the changing density when you go deeper. So then it becomes very simple. You can just use the simple formula with the deltas. Delta P, can you read this in the back as well? A bit hard. But if I click once, it's zoomed. The right one I can... No, but this is not in... There, oh, okay, sorry. So here we could say to 150, oh, that's too much. 75. This better? Okay. So, here we see, let's use the figure a bit still. Here you see we can simply use the hydrostatic equation, which shows that with increasing depth there's a linear relation to the increasing pressure. So what basically happens is you go to an increased delta PW, due to the water I've called it, at the floor of the tank, which we can calculate by filling in the depth of the tank. But if we want to know the total force on the wall, we have to take the average of that, which is half. So we first calculate this value and then use half of it to calculate the pressure. And then, I cannot go down with this one. Of course, we first always move to SI units, so meters and kilograms per meters cubed for the density. The area of the wall, we calculate that in squared meters as well. And then at the floor of the tank, we can calculate the pressure, and it becomes a very simple exercise basically. Because for the average, here this is the pressure at the floor of the tank, we use half for the average, and this half we multiply times the area of the wall of the tank, and then we get this, which is in Newton. Well, this is the pressure area Newton. And then we convert back to the tons that Anderson uses. I've called them the Anderson ton here, which is 2,000 pounds instead of the 1,000 kilograms that we normally use. So if we convert that to newtons, this is a pound, in English pound, times G, you get it in force, the lbf, times 2,000 is this. So this is 1 Anderson ton. So to express this in Anderson tons, we have to divide this answer by this, and we get 46.5. But this is a simplification, of course, because we've been talking about the increase in atmospheric pressure when you go down and the decrease when you go up, and we have completely ignored that here. So in the exercise, he basically asks for the force of the water on the wall. And if you were correct, you would add the atmospheric pressure here, because here the atmospheric pressure presses on the water. So if we only look at the force of this side of the wall, you would have to add the atmospheric pressure. It doesn't start at 0, there's no vacuum here, but it starts with sort of P0. But then, of course, you get a huge force, which cannot be what he means and is also not useful. But you could also look at the net force, the net effect, and then also take into account the increase in atmospheric pressure. Well, what did I use? Zoom once, and then we change it to 75. That was it, right? So, if you do, the real situation is more like this. You've got the pressure of the water on one side, you add the atmospheric pressure, not do it in the right scale, but anyway. Here the same on the other side, but you also get an increase of the air pressure when you go down. Well, we do not need the complex standard atmosphere equations for a height difference of only 3 meters. There we can use the simple hydrostatic equation as well. So if you calculate the sum here, you add this all up, of course those two compensate again, and the only effect is that you get a reduction of water pressure due to the increase of air pressure. Well, what is the net effect? He doesn't state at which altitude you are, So apparently Anderson didn't mean for you to even use the atmospheric pressure, but if you do, and we use the standard density of the air at sea level according to the standard atmosphere, you get 46.4. So it's in the order of 2 promille, 0.2% of change. So you see that the effect is indeed minimal because water is 1,000 times as heavy as air. Is this clear? So probably you tried ways that were much harder, and in the end it's not that hard. You can use simply the hydrostatic law, and you have to take care of the average. 3.8, shall we have a quick look at that one as well? That's a PDF, that should work better. Rather have it in the full screen, but okay. Can we go to full screen here? No? Let's go to a separate window then. Get it. Save a copy. Okay, well, let's just do it like this. So the question here was the change of air pressure per time. And what he gave, answer were two things, the altitude, 25,000 feet, and the vertical speed of 500 feet per second. So if you calculate those, you first convert to SI units, 25,000 feet, we're well within the first layer. That's always lucky, so we only need to go through one calculation there, atmospheric calculation. We're under the 11 kilometers. The vertical speed, 500 feet per second, we convert to meters per second. By multiplying the feet with 0.3048. So 1 feet is 0.3048, so we multiply this number by the feet to get the meters. If we then use the hydrostatic equation as we use it in the atmosphere, then you can see that if we change this, you can see that the dP dH, so the change of pressure per altitude, is minus the air density times the gravity acceleration. But we needed dP dt. Well, the nice thing is that if we want dP dt, we just multiply dP dH times dH dt. This is the change of altitude, the change of pressure per altitude. These two disappear, so that's exactly the same. This one we know, density times gravity. This is the vertical speed. So it's basically a multiplication of the vertical speed and this. Well, then we have to watch the units again. And we, of course, then have to calculate the density. Or take it from a table, but that's no fun. So let's calculate it. And also, with all these different atmospheres, it's always better to calculate it yourself. Here we first calculate the temperature, then we use the atmospheric formula for the troposphere. We fill it in, we get the air density, 0.54, already going down halfway, that seems reasonable. And then we just multiply the two to get the real answer. We take the density, the G, the vertical speed, and we get a change of minus 820.3 Pascal per second. But now, he comes up with this strange unit. He wants the answer in pounds per, what is it, pounds per feet squared second or something. Well, there it's not obvious immediately whether it should become larger or smaller. So the best way is then to be a bit careful with the units. Let's first calculate what 1 pound force per feet squared second is. We just make for pound force, we fill in pound times G, feet times feet. So here we fill in the numbers. And we get that one of these strange units is 47.897. So if we now divide our answer, which was Pascal per second, by this, by one of those strange units, we should get the answer that is stated in the solution, the American solutions. And you see that it's minus 17.13 instead of 17.17, and that's because in the solution on the web, all the intermediate answers are rounded off to 3 digits or something, and I tend to carry a few more digits with me along the way. So this is rounding off. Also, the decimal point is often hard to see in those solutions, so the PDFs aren't that great a quality. So at first it looks like it's 1717 or something. But just divide the answer by this, and we get this in a strange unit. And that's as simple as it is. Any more questions, you can always email me. and I will try to put better solutions on the blackboard.
Please visit our OpenCourseWare website for more information. See you at our next podcast.